So we want to look at optimizing with a quadratic objective. Okay, so remember what we've done so far. In 2 dimensions, we've looked at feasible region with inequalities, and as long as that, they make an area, we're going to see something could do all sorts of things, but we'll kind of go like that. So there is our feasible region. And so we looked at something like that in Module 4. Then in Module 5, we added a linear objective. Okay, so and I'll put over here linear objective. And we either want to maximize or minimize, and depending on what that objective function draws as, but we might have something like this. Maybe that's z equals 10. Here would be z equals 20. Those are supposed to be parallel, and maybe then that maybe is z equals 28 or something along those lines. And this is optimal, okay? Or it's our, in this case, a maximum, all right? So maximum, because they were getting bigger. And so we looked for sort of that biggest value of z that was just barely touching the feasible region. And with linear objectives, that's going to be how it works. Now, in also in Module 5, though, we had a feasible region with one equality. And remember that, so we fixed the number of counselors at 15. And so in that case, well, because of that equality, it becomes just a line, not a shaded region. And, so you could have something like this is now our feasible region. That's terrible. Let me erase that and try again. Well, sort of better. That's supposed to be a straight line. Okay, so there's our feasible region. And then again, we might have a linear objective. So, and linear objective. And so, we had different values, and maybe this is z equals 25. Maybe this is z equals 20. And then if we come right there, z equals maybe 16, who knows. And in this case, then it looks like this is a minimum we were trying to do, because that's the smallest. Minimum, there we go. And so again, this is our optimal spot here, where we can read off our x's and y's. And again, it's that same idea. We had our objective function that in this case, we were trying to make very small. Could have been trying to maximize it, but we were trying to minimize it. And we get right down here to the edge, and that would be the best we could do because it's got the smallest value of z that still touches our feasible region. Okay, so that's what we've done. Now, with quadratic objective. Now, this could look a lot of different ways, but for us, anything decent that you're going to work with, okay, the quadratic objective function is now going to look something more like this, okay, and so maybe this is z equals 20. And again, for us, most of the time, it'll probably get smaller. Z will get smaller as the ellipse here gets smaller, but it doesn't have to. It could get bigger. A lot depends on, if you think back to quadratics, is the quadratic opening like that, or is the quadratic opening like that? Right? So if you think of this distance across here, right, that's getting smaller, and so is the value of y. But here, as that distance gets smaller, the value of y gets bigger. And so either one could happen. But let's say, you know, this is z equals 15, and, you know, you could have one in here that was maybe z equals 10. Okay, so if we had something like this and we were trying to minimize, we'd want to be heading in there toward the center, which would be 0, z equals 0. If we were trying to maximize, right, you know, so we're heading here we're trying to make it as small as possible for a minimum, but we're trying to head out this direction if we're trying to make a maximum because z is getting bigger. Okay. Now, what could we have? So we could have feasible inequalities. Okay, feasible inequalities. And so again, you know, we might have something that kind of looks like this, and this is our feasible region in here. Okay, now I'm going to erase that because we might need that. Okay, so now let's draw, and I'm going to do another one of these beside it for kind of contrasting a couple of things. So here's our same sort of feasible region. There we go. Similar anyway. Now, a couple things could happen. You know, say we're minimizing, and say the inside is smaller than the outside. Well then, you know, what could happen could be that we might get ellipses for different values of z that do something like this. And so with a quadratic, the minimum might not be at the edge. On the other hand, if the center of those ellipses, so I'm going to put the center first and start drawing some ellipses like that, well then that one, well, if I can get it to just barely touch, okay, there's the minimum or optimal in this case for the left one, but here it is at an edge again. So minimum or optimal. Okay, and I'll put some z values on here to hopefully, say this is z equals 20, z equals 15. Maybe this one here then is z equals 13. And maybe this is z equals 20. Whoops, 20. There we go. Z equals 15. Z equals 10. And all the way in here, that dot is z equals 0. And so it could be 0 there. But you see, you could have a couple different cases where and this won't happen with straight lines, but with these quadratic ones, you could have one of these two cases where the minimum, or it could have been a maximum, either way, but the minimum could be totally inside the feasible region, or it may be at the edge like it was for the linear case. Okay, but it's hard to know until you actually work with it, and so you just have to kind of look at that for each case. All right, so that's with inequalities. Now, with one of them being an equality, so if we have feasible with one equality, then I have something like that. I'll draw it again over here. Now, in this case, pretty much you're going to have, again, most likely one of these two cases. Now, I'll probably draw a third when I'm done just to show you, well, you could have something else. But suppose we're trying to do a minimum, and there's the smallest point, and then we've got stuff like this. Well, we'll put that right there and touch it, and then like that. And we'll say, maybe that's z equals 10. There's z equals 5. There's z equals 15. Well, again, right there, if, say, we're trying to minimize, because these are getting smaller. That was a 10. There's our optimal. And notice it doesn't happen at either end of this thing. Okay? So that could happen for our optimal, because it's the last place these ellipses touch as I make z smaller. Now, another thing that could happen is, well, if that, I'll put that center like way down here somewhere, then what's going to happen is, so maybe this is z equals 20, z equals 15, z equals 10, and we'll put another one out here, maybe z equals 30. And again, if we're trying to, let me write down minimize for these, because if we're maximum, we need the biggest value. But if we're trying to minimize, we want the smallest value. And so in this case, it is right at the end. Okay, so either of these could happen with this quadratic case. And again, won't happen with the linear case or the straight line. If it's a straight line, it's going to be at one of these two endpoints. But with a quadratic, it could be somewhere in the middle, like this is, or it may be at the endpoint. A lot just depends on where the center really is of these ellipses as you make them bigger and smaller. Okay, so that pretty much sums it up. But I will point out you can have one sort of weird case that also may put it in the center. But if this is your feasible region, it could be the center of your ellipses. Is somewhere right in there. In which case, that again would be optimal if we're either minimizing or maximizing, because that's the center. So, it can happen. It's probably not real often something like that would happen, but more likely you get one of these two cases. So that is how a quadratic objective function will change things, is that it is possible we will not be at the edge of our feasible region. So here, if we have a case like this on the left, our optimal ended up being, that last place it could touch, if we were minimizing, was somewhere in the middle here. Whereas this case on the right, the last place it could touch was at an endpoint. Similarly, up here, if we had all inequalities, so we had a nice big region like this, then once again, that minimum might be somewhere in the middle of all this, as on the left, but again, it might be right at along one of these edges. But even here, notice it's not at a point. Right, it's somewhere along the edge, but not at one of the corners. All right, so that is, again, this idea of a quadratic objective.